Okay, so in this video, we are continuing on with our circle theorems on arcs and chords, and we'll be able to finish off the rest of these ones in this particular video. Once again, these are written generally as formal proofs, so if you want to have a go at these, you can always pause the video and have a go at proving it yourself, then checking with me, but I will be quite rigorous in the ones that I'm writing out, particularly when we're dealing with our congruent triangles, as we've done in the previous video. Now, this first example, we're told that a line through the center of a circle to the midpoint of a chord is perpendicular to the chord. So you're told here in this question that O is the center of the circle, BEC is a straight line, and we're told that BE equals CE. We want to prove that OE is perpendicular to BC. So we're going to use congruence again. So we're basically going to extend from the origin out to the points B and C. You can see this is where this dotted line is. This forms our two triangles. So we're going to introduce them here in triangle OEB and triangle OEC. Now, we have been told that BE equals to CE. So I'm just going to write that here and then write that it is given. I also know that OE is common. Don't need that. And I also know that OB is equal to OC because they have equal radii. Now, because of those three things, we can therefore say that triangle OEB is congruent to triangle OEC. And the reason is side, side, side. Now, we can therefore say, in a similar way in which we've been doing so far, that OEB, angle OEB, is equal to angle OEC. And these are corresponding. We know that corresponding angles in congruent triangles are equal. Now, we know, though, that BEC is a straight line. Now, because it's a straight line, we know that the angle sum on a straight line has to be 180. Now, since OEB equals angle OEC, these must equal 90 because this is a straight line. Because they both equal 90, therefore we know that OE must be perpendicular to BC. Okay, so moving on, since we've proved that, we can now, given that these two sides are, well, these two parts along our chord are 6 centimeters, we can find the size of OEB. So we can say, from what we know from this theorem, that OEB equals 90 degrees. And the reason is that the line through the center bisecting the chord BC is perpendicular to the chord. Okay, remember, we're proving the theorems, then we are using it to find unknowns. Now, we're given another circle theorem. This is saying that chords equidistant from the center of a circle are equal in length. Now, we're told that OP equals OQ. O is the center of the circle. OB is perpendicular to AB. OP is perpendicular to AB, and OQ is perpendicular to XY. And we want to prove now that AB is equal to XY. We want to prove this theorem that the chords equidistant from the center of a circle are equal in length. Now, once again, we've drawn in these dotted lines, AO and YO, in order, once again, to make these triangles. Now, since we've joined these up now, we've made two triangles. We've made triangle AOP and YOQ. So we're going to introduce them. We're going to say that OP equals to OQ. And the reason is that it's given. We know that OA equals to OY. We know this because they're equal radii. And we know that angle OPA is equal to angle OQY. The reason is that we're told that these are perpendicular lines. So we know that OP is perpendicular to AB and OQ, OQ is perpendicular to XY. All right, now that's enough information now to say, therefore, triangle AOP is congruent to triangle YOQ. And the reason is RHS, because we have a right angle, we're told that, we have a hypotenuse, those are the equal radii, and we have the two sides that are given. So now that we know it's RHS, we can therefore say that AP is equal to YQ. We know that corresponding sides in congruent triangles are equal. Triangles are equal. And AP is equal to PB. We'll say why in a moment. Now, thinking back to a previous theorem we've proved, we know that the interval through the center perpendicular to the chord bisects the chord. So that means that AP is equal to PB. That's a theorem we've proved before. The interval through the center perpendicular to chord AB bisects the chord. Okay, so we know this. We similarly know, now it's going to be a lot of writing here, okay? So we similarly, because of those exact same reasons, to save us some time, because we're already writing a lot, when we write similarly, it says that by that same logic, XQ is going to equal to YQ. Now that we know this, we can say that AP equals to PB, which equals to YQ, which equals to QX or XQ. And we know that since AP is equal to YQ, and that was proved above. Therefore, AB must equal to XY. So, as we get through these, you'll notice there is a lot of writing, but we need this type of rigor when we are dealing with these proofs for our circle theorems. Now, we know this, so we're just using it in this example. So we're trying to find the length of XY. So we know that AB, this entire segment, AB, since AP is 5, AB equals 10. And our reason is our line through the center perpendicular to the chord AB bisects the chord. So if we know that this length AP is 5 centimeters, then BP must be 5 centimeters as well. Therefore, AB equals to 10 centimeters. So therefore, XY equals 10 centimeters as well. And our reason is the theorem we just proved. So the chords equidistant from the center of a circle are equal. Good, okay, very last one, then we'll wrap up. Now, our last theorem that we're proving is that equal chords are equidistant from the center of the circle. So given a bit of information, GF equals to HI, O is the center of the circle. We're told that a couple of these are perpendicular and we want to prove that OL equals to OM. So we're going to join up OF with O and OI. So now we get our two triangles that we've just formed. So we're dealing with the triangles that we are going to introduce in a moment. Now, one thing before we say anything, we're going to make note of the fact that FL equals to GL. The reason being that the line through the center perpendicular to the chord FG bisects the chord. Okay, we have to make that statement first. And similarly, we can say IM, for the same reason, is equal to HM. Now, by making that note, we can say, therefore, that FL equals GL equals IM equals HM. Okay, with that in mind now, we've joined up OF and OI with these dotted lines, and we can introduce our triangles. So triangle FOL and triangle IOM. And we know that FL equals to IM because we've proved that above. That's why we did this kind of pre-work, because now we're going to use it in our congruence statement. So FL equals to IM, and we can write here proved above. Okay. We can also say that OF equals to OI. Equal radii. Now from there, we can say also that angle OLF equals angle OMI. The reason we know this is we're told that some of these are perpendicular. So OL is perpendicular to FG and OM is perpendicular to IH. With that in mind, because we know those three things, we can therefore say that triangle FOL is congruent to triangle IOM. The reason is RHS, because we have a right angle, we have a hypotenuse, we have a side. Therefore, we can say that OL equals OM, because the corresponding angles in congruent triangles, scroll down a bit, are equal. Cool. Okay, so now that we've done our very last proof for this video, we are just going to apply this proof. So we're just trying to find the length of OL on this one. Let's call it X. So we know that IH equals FG, which equals 14. Now, since we know that those chords are equal, we can say that OM equals OL, which equals to 5. Because equal chords are equidistant from the center. Okay, so that brings us to the end of talking about our chords and arcs, and we'll move on in our next couple of videos to talking about angles in circles. Thank you so much for watching. I'll see you next time.